Okay, so this is the only unit we'll be doing things from the 4 vector notation. Okay, so rest of the things we'll be doing simple potential problems. You are having given a given charge distribution, calculate the electric field by different methods. Okay, like Green's functions, like methods of image. Okay, and the other techniques. So if you are afraid of this thing, you are scared by this kind of notation, you should not worry. You try it at your places repeatedly, you'll get, okay, you know it better then. You'll appreciate these things in a better way. So let's take let's figure out the usual law, the force equation what we know. Okay, we will take mu is equal to I is equal to 1, 2, 3. That means the special components we'll be figuring out. Okay? Let's try to figure out the special components of this very equation. The temporal component will give us nothing. Okay? Why? If you remember this mu, that's equal to, what is the temporal component? 1 divided by root of 1 minus d square by c square. Another is d by c. 1 minus d square by c square. So this is our velocity for vector. Okay. So there is no number. No velocity vector here. It is here. It is 3 velocity. We are trying to figure out the dynamics of that 3 velocity vector. Okay. The equation of motion corresponding to that 3 velocity vector. That's why I am taking the special components of this very equation. Okay. So let's write. So I am having this MC GUI by GS. That's equal to E by C F. Okay, mu I am taking as I. Mu will remain as such. Okay, because it's a dummy index. Okay. So now let's sum over this thing. So you are having I. So let's sum this very object. That means let's take 0. The second term is Fij Uj. Okay. Got it? So J is a special component. So there is a sum over J in this case. Sum J. Okay? Clear? Any problem? So let's write the right hand side first. So it is E by C. Now tell me, what is this Fi0? What is Fi0? Yesterday we have done it. It is simply the ith component of the electric field, is it? Okay. So Fi0 is simply Ei. What is U0? 1 divided by root of 1 minus V square by C square. Is it? Okay. Now let's write. What is Fij? Yesterday? What is ijth component of F representing? These are the magnetic field vectors. Sorry, the components of the magnetic field. Is it? Okay. So then, how they are related to magnetic field? Fij. So anybody? So you are having epsilon ijk bk. Is it? So this is Fij. What is Uj? It is the jth component of U, is it? So what will be that? So it will be simply Vj. I am simply writing the jth component of U, okay, by C root of 1 minus V square by C square. Clear? Okay. Okay, so let's simplify this right hand side. So that's equal to, okay, let's take this root of 1 by V square minus C square common. So it is 1 divided by, or rather C times root of 1 minus V square by C square. It's there. Is it? No, yes. So there is E by C, I should say. Okay, you can keep, okay, let's keep E here. So it is like this thing. So I am having EI only. Then you are having this very object to 1 by C epsilon I j k, okay, bk, and then bj, jth component of the velocity. Okay. Now can you tell me what this object is? So this I can write. Let's write epsilon I j k bj, the second component, because these are the components I can interchange two, is it? So now what this is? So this is simply a cross product of B and B. Is it true? Samushan? So sorry, so it will be actually, I should say it is the ith component, because it will be simply what? Epsilon ij, ith component of this B cross B will be this epsilon, Bj and Bk, is it? Samushan? So that means this very object represents what? Ith component of the cross product of velocity and magnetic field vector. Okay. So therefore I can write this as E by C root of 1 minus V square by C square. So EI plus 1 by C and V cross B. Okay, it's I. Okay. Now let's look at the left hand side of this very equation. Okay. Let's write it. You are having, or I can write MC. Okay, what is GUI? Now tell me. So you are having like this thing, D by DS. Now what is DS? CGG, is it? So it's acting on UI. UI is what? Okay, tell me. So it will be ith component C divided by. Sorry, there is a factor, so it is C root of 1 minus V square by C square dt, because ds is what? So what is our ds? C root of 1 minus V square by C square dt. Is that true? So much on? Okay, and this d by dt, because this is a derivative, it is acting on the ith component of this very object. Okay, so that's equal to this E by C root of 1 minus V square by C square, okay, EI plus 1 by C V cross B, okay. Now this very object, okay, C and C cancels, root of 1 minus V square, so this very cancels with this very object, okay, and you are having this very C, this C cancels it, this C, okay. Okay, so let's write it what remains there. So I am having this object M G by dt, okay, then you are having Vi by root of 1 minus V square by C square, it's equal to E times EI plus, okay, E by C V cross B. Okay, now what is this M? It's a rest mass energy, sorry, it is the rest mass of the particle. You can take it within the derivative. Okay, so this is a constant term, this M. Yes, any question? Any question? So now tell me, I can define the latest momentum, 3 momentum, I mean. So I can define it as mv divided by root of 1 minus V square by C square, which implies its ith component I can write mvi root of 1 minus V square by C square. What is this object again? It's d by dt of pi. Okay? So therefore we are having this d by dt pi, that's equal to E I plus E by C, okay, B cross B. So in other words, I can write it as a vector equation d. So these are all the ith components, so it is simply E plus E by C cross. Okay, so this equation you know, huh? Here it is for the latest particle, because what is the momentum? It is the latest momentum. Is that true? Clear? Now let's take the non-relativist limit. So that means this equation is valid for both relativistic as well as the non-relativistic cases. Okay, you will see it. So we are taking the non-relativistic limit. So what is that? I am having V by C, that is small. So it implies this vector P, so which is mv by root of 1 minus V square by C square. This goes simply as m. Is it? In the non-relativistic limit, so this is equal to mv because this is very small. Is it? So much sure. So V by C is small. It is 1. This very objective. So we have this dV. So it's again the same equation. Okay. So now here it is okay. Let's write it as a non-relativistic. Okay, let's forget. So this momentum is the momentum of a non-relativist particle, and this momentum here is momentum of the relativist particle. So that means the form of equation is same, whether you are having a relativist particle or a non-relativist particle. So your equation of motion is same. Just you need to adjust the momentum of the particle. Okay, you take it relativist or non-relativist. Okay, clear? Okay, so now let's move. This equation we have derived from the covariant form of the equation. Now let's start from the Lagrange itself and try to derive the equation of motion, the same equation of motion. Okay. Although you have done that equation somewhere, but let me do it again. I think you have done it in classical mechanics somewhere. What's our Lagrange? So our Lagrange is equal to minus mc square root of 1 minus V square by C square plus E by C E dot V minus E. Okay? So while A is the vector potential and phi is the scalar potential. Clear? Okay. So what is the ideal Lagrange equation? So my ideal Lagrange equation is, which we know from classical mechanics. So that's like this objective. So what it is? Partial L by partial Q dot, and Q dot is actually velocity, is it? So it means the velocity V minus partial L by partial R. Okay? That's equal to 0. In other words, this is actually the gradient of L, I should put. So this is actually the gradient of L. Okay? Clear? So it's partial L by partial Q. Okay? Okay, let's write partial L by partial R. Sorry, let's write partial L. It doesn't matter. Okay? So let's figure out these quantities. So can anybody tell me what this object represents? Partial L by partial V and partial L by partial Q dot? It represents generalized momentum of the particle, is it? So I will come to this point in a moment. I mean, after deriving this very equation. Okay, so what is that? So if you see, this object does not depend on velocity. This depends on the velocity. This depends on the velocity. So I need to differentiate. So it is minus m square. So let's differentiate it. It should be 1 divided by root of 1 minus V square by C square. Then the differentiation partial by partial V of 1 minus V square by C square. Okay. Then I am having E by C. Okay. So it's A dot. So it will be simply vector A. Clear? So I told you what exactly this means. It means I am doing the component wise differentiation. It is partial L by partial VI. I am differentiating with respect to the ith component of the velocity. Okay, because it's a vector, so then you put it as a vector. So that is how we do it. So now can you tell me what this object is? So it is minus mc square 1 by 2 root of 1 minus V square by C square. So it's minus twice Okay, 2 by c square, what this is? So it will be simply vector v. Is it? Because what is v square? It's v dot v here. So it will be simply vector v, okay, plus e by c. Okay. So therefore I am having this partial L by partial v, okay, that's equal to, so look here, so all these factors will change, cancel, so you are having mv divided by this object, that is the relative momentum. Okay, let me write that as a vector p. So by small p I will write it, so plus e by c. So this object, entire object, this is the generalized momentum of the particle. P is the real momentum of the particle. So if okay, if you don't have the field, let's say P is equal to 0, the momentum will be simply given by this P. Okay, so the sum of these two terms is actually the generalized momentum of this very particle. Okay, we'll come to this point in a moment. Okay, what I need to calculate then? This very object, partial L by partial R. Let's calculate it. So it's a little bit tricky. Okay. Okay. So let's calculate this partial L by partial R, which I can simply say is actually the gradient of L. Okay. Is it true? So I can say it as a gradient. Okay, now look here. Velocity does not have the explicit R dependence. Okay? Velocity does not depend on what? Explicitly. Okay? So, but this A is a quantity which depends both on space as well as time, is it? And phi also depends on space and time. That means both they are having R dependence, these two terms. So if I take the, now the gradient of L, this will not contribute. I will be having this very object, E by C, gradient of the dot product of this very object, minus E gradient of phi. Clear? So what I need to calculate? Gradient of A dot V is A dot V. Okay? So we need to calculate. So there is an identity. So this kind of identity, I asked you to do it. Has anybody done it? Yes? Has anybody done it? Huh? You have done it? What is the value? What is the formula?
A cross L cross.
Yes, A cross. So A cross.
L cross B.
A cross curl of B. Then plus B cross curl of A. Then
A dot
what is the sign? Plus. Yes.
A dot L
A dot del
B
acting on B, then
plus B dot L
B dot del. Okay. Are these two terms correct? Yes. So everybody, it is great. You have done it. So everybody has done it. You are able to do it or not? Then I will derive it again here. Just raise hands. You want me to derive it or not? No? Okay, let's proceed. So this implies you are having now gradient of A dot V. Okay. So what it is equal to? Let's write what is A. So it is this A cross curl of V. Okay. Plus V cross curl of A. Okay. Plus what is A? It is A dot this very object, then acting on V, plus V dot this object acting on. Okay. Now tell me, among these four terms, which terms are zero? Huh? A dot? A dot L? Huh? Yes?
A dot L and A plus
No. A dot del, huh? So you mean this very term? Why it is 0? Yes, you have to justify, huh? Why it is 0? It's true, it's 0, why? V does not have an explicit R dependence, is it? So this is simply the differentiation of, okay, forget about this A. So this is a differentiation of V with respect to coordinate, is it? Is that true? So it implies, since this does not have the coordinate dependence explicitly, so its differentiation is equal to 0, okay? So this very object is equal to 0. And which other term? Del cross V, because this is again the differentiation, is it? Curl of V means you are differentiating the components of V, is it? So this is again equal to 0. Since V does not have explicit R dependence. Okay? So therefore we can write this object A dot V is equal to V cross curl of A, okay, plus V dot okay. Clear? So is there any more approximation we can do? Can we do any other approximation? Okay, so let's substitute it in the formula. So we are therefore from Euler-Lagrange equations we have d by dt of what? Partial L by partial V, is it? So what is that equal to? P plus E by C A. Okay? That's equal to this gradient of L. What is gradient of L? E by C. Okay? Multiply. Okay? Gradient of A dot V. That object is this. So it is V cross curl of A plus V dot nebula acting on A. Okay? Then you are having minus E like this. Is it true? Is it true? So it is simply what? Partial, okay, d by dt of partial L by partial V, that's equal to gradient of L. Okay? So this is what I have done. So now let's write this thing. So it is dE by dt, okay, plus E by C, dA by dt, that's equal to this object, E by C, okay, B plus, what is del cross A? It is B, is it? So let's write B, okay. Okay, let's write it later on. Let's put it this way. V cross A plus V dot nebula. Okay? So now let's evaluate this very objective. dA by dt. This is the total derivative of A, is it? So much else. Now let's evaluate this objective. What is dA? What is the total dilation of A? A is the function of what? Function of R and P. Is that true? What is that equal to? Okay, can anybody? Yes? Partial A by partial T dt. Is that true? Then plus partial A by partial R. What is that? What will be here? Anybody? Yeah, yes, it's true. Yes. So gradient of A, is it? So it will be simply gradient of A dot So this implies then dA by dt. So that's simply equal to partial A by partial t plus. So when you divide this by t, so it will be lost here. So I can take it this way. So we can write d dot delta. Okay. So much on. Exactly, I should. This is not correct to be divided. It is this way because it is a gradient. Like this. Can you tell me why? Why that's not the correct way to write it? Anybody? Gradient acts on a scalar, is it? Assumption. Okay. So I had put actually gradient acting on the vector. So this is the correct way to write it. Clear? Now you are having dr dot delta. It's actually a scalar quantity and operates simply a scalar operator, just the differentiation acting on the vector A. Okay. So now let's write it here. So you are having this dp by dt. Okay, plus E by C. Okay, what is dA by dt? So it's partial A by partial t plus V dot delta acting on A. Okay, we put it this way. Is equal to E by C, V cross del cross A, okay, plus V dot del acting on A. I think we have missed one term in this, so there is a minus E by del. Okay? Minus E. Okay, now this very term cancels with this very term. Okay? So I can write dP by dt, that's equal to, that's right. So you are having minus E del phi minus E by C partial A by partial t, and then you are having another term E by C V cross del cross. Okay? Clear? Is it? So now you are having two terms here. Okay, two types of terms. Now this very term, okay, the first two terms, they are independent of the velocity. Okay? Okay, and this term it depends on velocity. Clear? So much now? So because there is velocity is explicitly here. You don't have the velocity vector here. Phi does not depend on velocity. Okay, A simply depends on the coordinates. Clear? So this is a term which depends, which does not depend on what? The velocity. Okay? We define a quantity. So this very object E minus del phi minus 1 by C partial E by partial T. Okay? So plus E by C V cross del cross. So we define. Okay, so now tell me what is dP by dt? It is simply the force acting on a particle, is it? Now if you are having a velocity independent, okay, so these two terms, this is also a force, this is also a force, is it? So it means I can define force acting on a charge E, let's say per unit charge E. So what that will give me? That will give me the field corresponding, is it? So that will simply give me the field, intensity of the field. Now, if you are having a force that is independent of the velocity here, so you call that as an electric field, okay? Force per unit charge, and if that force per unit charge turns out to be independent of velocity, you call that as an electric field, okay? So we call that electric field as E minus lambda phi minus 1 by C partial A by partial T, and the another term gives me the force that depends on the velocity and the force per unit charge that's dependent on velocity. We call that as the magnetic force, and we define the magnetic field vector to this object here, where dP by dt, that's equal to, okay, that's equal to what? E times vector E plus E by C. Okay, so this is the Lorentz Force equation. Okay, what you know. Any question? Any question? Now let's look at the Newton's laws. So you are having this very object. So this is the Newton's equation of motion. Is it? Any question? So now if you are having certain motion, let's say if you change this t to minus t, okay, what will happen? So this f will remain same, is it? So if you change t to minus t, okay, so it is the quadratic here, so this force equation remains same. What does it mean? Suppose it means if you are having certain motion possible, let's say in certain amount of time, let's say forward time, let's assume from 0 to t, a particle is executing certain motion, okay? Now if you reverse the direction of the time, okay, or if you reverse the motion, so that's again possible. So if you go from, let's say, 0 to minus t, that means simply the reflection about the time axis. So think it in this way, you are having some ping pong ball, okay, simply Costco ball, what you know, okay, you drop, forget about the friction, you drop it from certain height on the floor, what will happen? It will come to the same height, is it? Now look at the forward motion, so dropping of the ball and coming back, is it? And then observe the reverse motion, is it? So do you feel any distinction? No, you don't feel distinction. So that means if I can have a forward motion, a possible forward motion, Newton's law says the same backward motion will be there. So that means if you are having if you make a movie of that ball dropping down, you play it forward and play it backward, you will be getting the same thing. You cannot distinguish between what I say, the past and the future. It will be one and the same thing, okay? Now let's look at this very equation. Okay, let's look at this very equation, the Lorentz equation. Now if you are having a charged particle that's moving in an electric and magnetic field, a certain motion is possible, is it? Now let's reverse the direction of the time, okay? Let's change t to minus t, that means I am changing what? I am in future with the past, okay? So it's not the time travel, you should not, so those things are insane, okay? So let's take this t to minus, it is simply a symmetry kind of thing. We call this symmetry as a time reversal symmetry in a system, okay? Let's change this t to minus t, what will happen? So this occurs a minus sign here, is it? So, no, P occurs a minus sign, is it? P is the momentum. So if I change, okay, look at, so what will happen if I change t to minus t to E? What will happen to E? It will remain same because it will be same. If you, let's say, if you switch on the electric field, forget about magnetic field for the time being. If you switch on an electric field for a certain amount of time and you reverse the time, you will see you are having the same electric field because electric field does not depend upon the time. Think of a simple electric charge, okay? Its electric field is independent of time, is it? So it only depends on the space coordinate because at different points you will be having different, I mean the number of lines will be at certain point dense and other points it will be, I mean less dense, okay? So under this very condition, this E will be same as what? E, okay? Now what will happen to P? It will go to minus P because P depends on the velocity. Velocity will change the sign, is it? Velocity is simply dx by dt, okay? Okay, now what about the left hand side? So dp by dt will be invariant, it will not change, is it? So you are having a minus sign here and a minus sign here, it will become plus. So this will also not change. Now what will happen to this very object? So since P, okay, V also changed to what? Minus V, is it? So P changed to minus V, is it? Now what happens to V cross B? So that means V cross B gives me the sign change, is it? Now how I can make this invariant quantity? That means it does not change sign. If B changed to the minus B, is it? So it means under this time reversal symmetry, okay, I can have, okay, so I need, if I change T to minus T, that means if certain motion is possible in an electromagnetic field, if I reverse the direction of the time, what does that mean in an for a charged particle in an electromagnetic field? It means you keep electric field as same, okay, but reverse the direction of what? Magnetic field. So you reverse the direction of the magnetic field, you will be getting what? The same kind of motion. Okay, think of a circuit. Okay, you are having a charged particle in a circular motion. Okay, it is, let's say, let's think only the magnetic field. The circular motion is possible. What will be the direction of the momentum? It will be the upward. So if I don't change the field, I mean B to minus B, so let's say you reverse the direction of the time, I mean you take T to minus T and you don't change the magnetic field, what will happen? So you can distinguish between the arrows, is it? Samajh? You can distinguish between the directions. But if you change the direction of the field, what will happen? It will be the same thing. Look, it is this way. Suppose you are having a circle this way and the arrow comes this way and the observer is here, is it? So it will observe the circle and arrow coming this way. But when you change, when you make a mirror reflection, where will be the observer? Okay, but if you change, so it will be only possible if you change the direction of the field, is it? So you will be getting the same kind of circle with the same arrow, is it? So that means you will not be able to distinguish between one side with the other side, okay? Samajh? So this is a very important symmetry, this time reversal symmetry. It allows us, I mean, we are not able to actually distinguish between future and past. Okay? Future and past are one and the same thing. Okay? It is simply our observation. It may, okay, for a given kind of motion, it is simply our observation. I mean, because we are locally in certain region where you say you are having a future and you are having a past, is it? Think of an intergalactic space. Let's put it here. I mean, let's put this way. You think of an intergalactic space. What is the time there? How you measure it? Let's assume how you distinguish between past and the future. An event that happens in the past and an event that happens in the future, is it? So you are not able to actually distinguish between the two. They are one and the same thing. But there is only one kind of mechanics that helps us to distinguish between the two. Anybody? That is the second law of thermodynamics. I mean, thermodynamics is only this kind of system where you can actually distinguish between future and past. Okay? Do you know how? Because temperature always flows from hotter object, or the heat flows from a hotter object to the colder object. There is no reverse way. Huh? So that's actually the entropy change, I mean to say. So that's exactly the same thing. I mean, only the hotter bodies lose energy and the colder bodies absorb the energy. Is that true? So you don't have the reverse way. So you are able to distinguish between what? Future and past. Okay? So this is only the system which distinguishes between the two, but rest of the physics, if you are having, okay, this kind of symmetry, it will be useful in your course, this particle physics course, while you will be doing the muon experiment. Okay? Detection of the muon, okay? Parity violation. Have you heard that? Okay, so probably in the next semester you will be able to understand it, how we actually describe the, I mean, experimentally how we detected the parity violation in muon experiments. Okay? So much, and that was awarded Nobel Prize in 1950s. Okay? So let's go back to the Lagrangian and calculate these quantities, which I forgot yesterday to do. So you are having this minus mc square root of p. By the way, there is nothing like time travel. Okay? I mean, this argument usually people, I mean, mistakenly relate with, I mean, the time and the time travel. You travel in the past or you travel in the future, is it? Okay. So it's it has nothing to do with that, and it's not actually possible because you don't. There is no definition of the future. Okay. So think. Okay. Think it in this way. You are having. Let's assume, and two persons are there. One is, let's assume, on Earth, and you send through a space shuttle another person to Mars. Okay. Or to some distinct place. Okay, where you can actually observe the time difference at least. Okay. Okay, put it this way. Suppose if I call you people, let's say you are at home and I will call you. So between my speaking and the time I speak to you and the time you receive my signal, is it? So there is a finite time lag, is it? Is that true? So that means with respect to you, I am actually in the past, is it? And you are actually in the future. I am sending my signal to the future. Samajh? But does it mean okay, now if there is a significant distance between the two where you can observe this much of time, okay? Let's say you send one to the another galaxy, and one second person, and he sends a signal, okay? After some amount of time, he will come back to the same place, okay? But let's say the signal, the time at which he leaves the second galaxy or the faraway galaxy, he sends a signal, okay? It may happen he may reach before the signal, is it? So then what will be the future and the past for him? Think of it. These are not Star Trek movies, they are simply physical problems, okay? So let's take, now let's define the generalized momentum. Okay, so let's write it by the capital P. Some people write it by pi. Okay. So what is that equal to? It will be simply equal to mv divided by root of 1 minus v square by c square. I will not derive it. You need to derive it by yourselves. Okay. Plus e by c a. So that's equal to the generalized momentum. It is equal to the real momentum of the particle, e by c a. So in other words, the momentum of the particle gets in an electromagnetic field, it gets shifted by this much. Okay. So let's say if you write the energy of a particle, okay, I will come to this one in a moment. Okay, now let's write the Hamiltonian. Hamiltonian will give you the energy. So it's not an operator, huh? These are simply numbers. Huh? Hamiltonian, when you say, look, you think as an operator, it's simply a number as a function here. Huh? So let's write the Hamiltonian. I will put it as an h for the time being. So what it is equal to? So it is v dot partial L by partial v minus L. Okay. So what is this v dot? Okay. So then you are having okay partial L by. So yes, it is. So let's write P plus E by C A, okay? Is that true? Minus L, what is L? So it will be plus MC square, root of 1 minus V square by C square, okay? Then you are having minus E by C A dot B, okay, plus E by 5, okay? So this objective cancels with this objective because it's V dot A and this V dot A with a negative sign. So what you are having? So P dot V, what is P? It's mv, so it is simply mv square divided by root of 1 minus v square c square plus mc square root of 1 minus v square by c square plus e phi. So just work out these two things. So you take m out, okay? So what it will be? Can you tell me? So it is simply mc square divided by root of 1 minus v square c square plus e phi. Okay, so this is the energy. If you see, this is actually the energy of a particle in absence of the field, is it? If let's say a field is equal to 0, so this will be the energy of a relativistic particle. Huh? We call this as a mechanical energy. Simply, let's define it as a mechanical energy. Huh? Okay, and okay. So in addition to this, we are having actually the potential energy coming, or the energy coming from what? The electric field. Samajh aaya? So this is our energy. Or the energy of, or energy. Let's write this energy. Okay, I will reserve this word, this E for the mechanical energy. Okay, so this is energy of a charged particle in electromagnetic field. Okay, so let's write it. Okay. So I can write this way, h minus e phi, okay, the whole square, that's equal to m square c raised to 4 divided by root of 1 minus v square, so 1 minus v square c square, and you can write this very objective, p square, okay. So what is p square c square? Can anybody tell me? Just tell me. When you say. So that's equal to this p minus e by c a, okay, whole square multiplied by c square. Is it clear? Is it clear? So now let's okay. So which implies therefore this h minus e phi whole square, that's actually equal to this p minus e by c a whole square c square, then anybody, plus m square c square. Is it true? Is it true? It's actually in the lowest approximation that the momentum is 5. So this will be home assignment for you people. Just show it. Yeah? So the rate of change of the energy is simply equal to v dot what? dt by dt. Clear? So it's in absence of the field. I am simply taking the rate of change of the mechanical part of the energy. Okay, what this will give me? It's simply the work done. Rate of change of energy is what? The work done by the particle, is it? Samajh? Now what is our dt? Okay, if you are in an electromagnetic field, so what is dt? So it is E times E plus E by C V cross V. Is that true? So what do you get? Simply V dot E. Is it? What about the other thing, other term? Because V dot V cross V is equal to 0. So that means if you are having a particle in an electromagnetic field, it's only the electric field which is doing some work on the particle. Okay, magnetic field does not do any work, is it? Clear?